Viswanathan?
Yes, please.
So shall we start the session? It's 11.
Yeah, please.
Thank you, sir. Thank you. A very good morning to everyone. I welcome you all to the 11th online lecture of the lecture series on science and engineering research leading to innovation, entrepreneurship, and scholarship, which is being organized jointly by CSIR, Indian Institute of Chemical Technology, and IEEE PES IAS PELS Hyderabad Joint Chapter, IEEE Guntur, and IEEE Anantapuramu subsections. The series is featuring talks by distinguished speakers on diverse topics to commemorate the contribution of scientists, researchers, technologists, and entrepreneurs as we celebrate Azadi Ki Amrit Mahotsav, the 75 years of Indian independence. I am Beniaz Ara Begum, project scientist at CSIR-IICT, your host for today's online lecture on process modeling and simulation. My heartiest greetings to our today's invited Professor Viswanathan from Department of Metallurgical Engineering and Material Science, IIT Bombay. We all know constructing abstractions of systems to facilitate experimentation and assessment is both art and science. The technique is particularly useful involving problems of complex systems where easier solutions do not present themselves. Modeling and simulation methods are currently used for a number of applications and in fields such as biology, cosmology, population dynamics, military effectiveness, and also in Department of Defense. Without simulation, study of these subjects may be inhibited by the lack of accessibility to the real system, the need to study the system over long time periods, and the difficulty of recruiting human for experiments. Because the techniques offer solutions to this problem, it has become a tremendously powerful tool for examining the intricacies of today's increasing complex world. It saves a ton of time, money, resources, and even human lives. It allows us to open a new panorama, as now our imagination is not the limit. Rather, what we input or output in the process simulator, we can test multiple case studies in order to verify the best case or the optimal condition. Our today's invited speaker shall cover a general introduction to modeling methodology and simulation, followed by some case studies from iron and steel making process. With this, we formally begin today's session. I request Professor Y.V. Sivareddy, Chairman IEEE Anantapuramu subsection, to give his welcome address and opening remarks. Professor Sivareddy, please.
I think Benias Shivareddy has not joined. I think he'll be joining it soon. I left a call with him. So I think maybe we can proceed with the introductions. They'll join a little later.
Okay, sir. Thank you. Now I request Dr. Yamuna Rani, Chief Scientist, CSIR-IICT, to introduce our today's speaker. Dr. Yamuna Rani, please.
Thank you, Dr. Benias. I also take this opportunity to thank Dr. N.V. Satyanarayana for involving me in this particular aspect. But before going to the introduction task, I would like to express my appreciation to this conduct of this lecture series of course, on this occasion of Dr. N.V. Satyanarayana, but it is a very good gesture. And rather than we have been used to having felicitations to the retiring scientists, superannuating scientists in terms of seminars which are conducted, which could be ranging from 1 to 3 days or 5 days. But having a lecture series over a period of time spanning over wide range with the gaps and as well as covering wide range of topics and across a wide audience is a very good gesture in this on this particular occasion, and that also covering areas, all areas, although they are wide range of topics, they are still falling within the scope of Dr. N.V. Satyanarayana's research, and that is really a very good aspect and amazing aspect of it. So I would like to convey my appreciation on this particular aspect, and also for to IEEE the collaboration which they have given in this particular regard. And now I move on to the actual task which has been assigned to me, which is introduction of the speaker of today's talk. Professor Viswanathan is actually presently heading the Center of Excellence in the Steel Technology Department of Metallurgical Engineering and Material Science in IIT Bombay. He has obtained his ME and PhD in Metallurgical Engineering from IISc Bangalore. And he has also been a visiting professor at several institutes abroad, which are including Royal Institute of Technology, Sweden, Luleå University in Sweden, where he also, Luleå University of Technology at Sweden, where he has also been an LKAB chair professor, and also at Abo Academy in Finland. He is not only an outstanding teacher who has received excellence in teaching 4 times at IIT Bombay, but in addition to it, his recent awards include Metallurgist of the Year 2019 award by Ministry of Steel, Educator of the Year award in 2020 by Institute of Metals, Indian Institute of Metals, for his and for his role in managing the campus during lockdown period. IIT Bombay has honored him specially with the COVID Warrior Award, which is also a very appreciative initiative. And Professor Viswanathan, in addition to his academic fervor, he has also gone into applications into industry, where he has done the simulation models, developed several simulation models for a blast furnace simulation tool along with Tata Steel. Probably there, Dr. N.V. Satyanarayana was also involved, and also for LKAB Sweden, and then for Precision Steel India Limited, Precision Steel India Limited. So these activities illustrate his in-depth understanding of the concepts and application-oriented manner also. He's also been an advisory board member for Steel Research International and Transactions of Indian Institute of Metals, and is a reviewer to several international journals of repute. I take this opportunity to invite Professor Viswanathan, and I am looking forward to a very enlightening lecture from you, Professor Viswanathan. Thank you.
Yeah, thank you. You can hear me?
Yes, sir, we can hear you.
Okay. So, first
Professor Viswanathan, one interruption. I think Akbar and Devjyoti, they have also joined.
Yeah, I saw that. Yeah, I'm
maybe both of you, can you put on your cameras? Okay for you, Akbar and Devjyoti. Yeah, Akbar is here.
Hello.
Yeah, long time. Yeah, long time. Yeah, good morning. Nice
very
to
nice.
see you. Yeah.
After a long time. I am in Mumbai.
Okay, where in Mumbai? Yeah.
It is in Chandiwali,
Okay,
Kapurdipalanji,
okay.
just besides IIT.
Oh, okay. Very near.
Yeah, Devjyoti is also here.
Yeah.
Hello, Dr. Bandhabadia. Yeah.
Yeah, Devjyoti.
Hello.
So we can start.
Hello.
Devjyoti, your mic is off. Mic is mute.
Your mic is mute.
Yeah. How are all of you?
Fine.
Nice to see all of you. Satya is the same. Good to see you.
I think we can go ahead now. We can have the interactions.
Yeah.
So, Viswanathan.
Yeah, sure.
So first of all, let me formally thank IICT team, Dr. Satyanarayana, Dr. Yamuna Rani, Dr. Benas Begum, and all others, and IEEE chapters I saw. So let me thank all those organizations to invite me to give this presentation. Of course, I am also very honored because I see a lot of eminent speakers among them. I also got the opportunity, so it's really a great honor. So thank you once again. So let me start sharing now. Yeah, I think I'm already sharing.
Sir, your screen is not visible. The PPT presentation.
Just give me a second. Maybe I have to share it again.
Yes,
Yes,
it is
sir.
visible.
Yeah.
Okay. So I'm going to talk about process modeling and simulation. So let me tell you that I started my journey into process modeling. Basically, I started as a physicist, BSc physics, where I used to really like mathematics and physics, and then I happened to end up in IISc, and then I saw, Professor Lahiri, who's my guide. Um, he was the one of the person who was talking a lot of mathematics in the class, and then I told him that I'll be, I would like to work with you, and that is the way my journey started on process modeling and simulation. And then, of course, afterwards, after my PhD, then I spent some time in Sweden, where I was very much involved, collaborating with somebody who was doing a lot of experiments, Professor S. Sitaraman. And that has also been a very great learning experience, because in this talk you will see that I'm going to discuss about both the aspect of experimentation as well as modeling. And then, of course, when I joined IIT Bombay, then my first project was, with NML. And at that time, I started interacting with Dr. Bandyopadhyaya, Dr. Akbar, and Dr. Satyanarayana. So my first steps towards, modeling in that sense, professionally, as is from NML, and especially my dream always have been to develop blast furnace is very close to my heart. So that has been always my dream, and I can tell you that at that time when we developed, we used to tell, in many of the meetings, the model which we have developed is like a baby, and it has to be allowed to grow. Even in the review meetings, that's the comment we used to make, because it is not a easy task. But now I can tell you, with all those experience, I continue to work with a lot of students. And now the model has become a young man, of course, it may need some more maturity, but it has become a young man, and all those experiences have really contributed to the blast furnace modeling. Of course, other than blast furnace modeling, I'll be also discussing other things in this talk. And I understand there are, people who are not really from metallurgical background, so I try my best not to get into the details, but at any time, especially I understand there are also a lot of young people, so anytime please feel free to interrupt me and ask questions. I don't have I'll be more than happy to answer those queries. Okay, so you can interrupt me, that is not a problem. Okay, fine. So let me, so the title I have given is Process Modeling and Simulation. So before I get into, the specific case studies, I just want to tell you, yes, please.
He wants to make a project. This
Hello?
is patent teacher, no?
Hello, am I, yeah, is it okay?
Yes, sir.
Yeah, okay. Yeah, I thought somebody is trying to tell me something. Yeah. So why models? Okay. So I look at models in two ways. Means one is to guide acquisitions of experimental information driven by a hypothesis. In some sense, I can tell you that we are all modelers. Means whether we do experiments, whether we do, modeling, in some sense we are all modelers, because the way science works is also through experimentation, and for this experiment, based on this experimentation, we hypothesize things, and we try to explain that phenomena in abstractive, through some abstraction or through some laws or whatever it is. So at the end, it's very difficult to say that somebody is a modeler, somebody is not a modeler. Rather, if you extend it philosophically beyond the science, even the way we interact with others is also in some sense modeling. For example, if I interact with someone, I form a model about that person in my mind. And, every time I interact with that person, I try to, keep changing my model. And of course, the model which is there in my mind, I have some expectation. And if the person doesn't, behave the way I expect, then I get unhappy. And of course, if the person behaves the way I expect, then I feel happy about it. In some sense, I look at it more philosophically that every time we do things, we are actually all modeling. Anyway, the other aspect is, especially when it comes to large processes, which is true when it comes to metallurgical processes. To understand complex system, we can use we can use modeling extensively. That also I will just to illustrate these points. You just look at metallurgical processes. Those who are not from the background, I can tell you that these are all very large scale, high temperature, highly heterogeneous. You put stones. For example, this is what I have shown is a blast furnace. You put stones at the top and you get hot metal at the you get metal which is liquid at the bottom. So these are all highly heterogeneous, complex, and the scale is also large. In a day, a furnace like this can produce 10,000 tons of iron per day. And as you may be aware, India is now the second largest producer of steel in the world, and we are more ambitious to become double our capacity and all those things. So a lot of steel plants are being planned and all those things. Just to tell you also, sometimes some of these things don't come in our news. Just 2 or 3 years back, a huge blast furnace like this, it's really huge. It was actually moved from its place, and another new blast furnace was kept on that place. It happened very close to Mumbai in a place called Dolvi. It's owned by JSW. It is being shown in National Geographic as an engineering marvel. You can imagine 8,000, 9,000 ton. The whole structure is being moved from one place to another, and then a new structure being kept. These are all wonderful things which one can learn, and a lot of engineers are involved, whether it is mechanical, chemical, or so many different kinds of engineers, and such tasks are being achieved very close to us, but quite often we are all not aware of it unless we see National Geographic, maybe our press and all those things. They don't highlight some of these things to a large extent. Anyway, so that's the scale at which we operate. And these are not easy things to understand and operate, etc. And on the other hand, as I was telling you, with NML, and that is the way I started my interaction with Dr. Satyanarayana and Dr. Bando, Dr. Akbar and others, where we wanted to bring down, the carbon emissions from the efficiency of the furnaces have to be brought down and has to be increased. That was the task. Of course, that task still remains. Only thing is now India is also signed to Paris Agreement. So these are some of the large furnaces which have a lot of carbon emission. So how to use more hydrogen into these furnaces, etc. All these things needs to be explored, and that can be done, through models, and models can help in that. I'll just show you some illustration for that. So when it comes to, such large system, of course, the traditional way of, or that's the way people have been doing is, you cannot look at all the aspect of the system. So you look at a particular aspect of the system, and that too, when the system becomes very complex, heterogeneity is high, and measurements becomes difficult, then, each one tries to interpret through, that particular focus and try to say that, okay, this is what the system is. Quite often I have seen this happens in large system. So it is kind of, the famous story, 4 blind men and an elephant trying to describe what an elephant is. Quite often in technical discussion, this is what, all of us have experienced. And the other point is, when systems become complex, and especially when it comes to metallurgical system where we are dealing with so many different variety of elements in the periodic table which behaves differently, quantitative becomes more difficult because there is a heterogeneity in that sense also. So because of that, because of those challenges, it becomes more qualitative, and that is also something which always, metallurgical engineering subject as a curriculum also has to deal with. But then modeling helps in make it quantitative. And not only that, if you have different aspect being studied, and if one makes it more quantitative, then models can help in, all these knowledges you can systematically integrate and look at the bigger system. So that way I look at models as something which can do integration of so many different things, knowledge which has been gained through different experimentation. Okay. So with this, let me also, this is one of my very famous, professor from chemical engineering, Professor Rutherford Harris. He gives a lot of maxims about modeling. Just I have taken some maxim from him, just to again give you a flavor of how to go about modeling. So one thing is, before one starts modeling, one should have a clear objective. Okay. See, the thing is, again, when it comes to complex systems, quite often models can be of different rigor. That means there can be a simple model, there can be a more complex model, there can be still complex models. So, and there is a tendency to believe that, the more complex model which will take all aspects into account is a better than one than as something simpler. But let me tell you, all models have their own place, whether it is simple or complex. Okay. Rather, depending on the objective, one needs to decide. Rather, as an engineer, in the field, quite often this becomes necessary because there is no point in over modeling something, overdoing something, because the cost is involved in that. So what is needed for the objective, according to that, the model has to be, made. So that way, one should have a clear objective, and based on that only one can have, what the model should do and how rigorous and what all things needs to be considered, that becomes clear. Because the other thing is, always understanding is important, As a modeler, though I like mathematics, as I told you, but when I do model, I see things happening inside the furnace. It is like one has to get into whatever system one is looking at. You imagine what is happening around there. You have to actually visualize and then form, equations, etc. Quite often, with a lot of this commercial softwares which are coming into existence, one of the things which I find among the youngsters is, okay, they start using things blindly without knowing actually what is inside. And this can be quite dangerous because, you don't know, whatever it throws out, it can be junk. So one has to be very careful. One needs to always, understand things and critically look at whatever software which one is using. And one should know what is actually inside happening. Then only it becomes, such results will be useful. Otherwise, it can be, you may not know whether you are even making a mistake. And the most important thing which I like, from Professor Aris Rutherford is avoid rigor like plague. It only leads to rigor mortis. You see, rigor mortis is when somebody dies, there is a stiffness which comes into the body. Okay, that is what is called rigor mortis. So actually, he says, when you look at complex system, we have a tendency to put all the things, I want this, I want that, and all those things, and you start very grand, rather, in the journey of modeling, I have done this mistake. You start a grand, I want to include this, that, so many things, and you start with everything being included. Then you see that the model doesn't move at all, it doesn't converge, or it is staying where it is there at you started it. It's not able to run at all. That's what he means by, avoid rigor like plague. You develop from simple, make it move, make it flexible, let it run, and then slowly add things. This is again a great learning I have throughout, this modeling. So many systems I have learned, and hence it is very important. Okay, the other comment I have to make is, again, modeling and simulation are not the same. Unfortunately, there are a lot of, people who confuse or who rather don't distinguish between modeling and simulation. Modeling is, if you have a reality, a physical system, as I told you, you understand the system, study the system through experimentation or whatever it is, and then forming an abstraction. This abstraction can be in terms of equation, in terms of, some statements, whatever it is. That coming from the reality, the actual reality to an abstraction is actually the modeling. And then once you form these models, how to, solve them or how to implement them, that is, of course, that is the modeling methodology. And once that is being done, then once you run the model to study different things, that is called the simulation. Unfortunately, many of us don't do modeling actually. We only do simulation because there are some softwares available. We put some, boundary conditions, this, that, etc. And actually we only do simulation quite often. We don't do modeling. Means modeling is done by people who really look at the systems and, try to abstract things. There is an abstraction involved in this thing. So this has to be really understood. Otherwise, this word modeling and simulation are being used without distinguishing what is modeling and what is simulation. Okay. So this is my last slide on general introduction to modeling. When it comes to, the principle used in process modeling, but this is not only in process modeling, as I told you, in science itself, that's the way we do. Is we can split them into two. One is conservation equation, like, basically it comes from, first law of thermodynamics, energy conservation or mass conservation, or it can be charge conservation, or it can be force or momentum conservation. So basically we have conservation equation, and then there are constitutive equation. Constitutive equations are, these are, you do experiments looking at a particular phenomena, and based on that phenomena, you make a law. For example, Newton's law of viscosity or Ohm's law. Many such law. You can say, how, suppose I put a stress on a material, how does it behave? So all these things are constitutive relation. So if you look at its conservation and constitutive relation is primarily we do in all our modeling. Okay, and specific to process modeling, we use extensively thermodynamics, principles of thermodynamics. And as I told you, since these systems involve a lot of mass, momentum, heat transfer, we use those principles. Again, it is all based on conservation and constitutive relation, reaction kinetics. Of course, it also have to develop this constitutive relation, one needs to have experimental observation. It can be at high temperature scale, it can be in the laboratory scale. And these models, again, please don't misunderstand that models are only mathematical. No. Models can be even physical models. These are again extensively used to simulate the flow of liquid steel. In such large systems, it's so difficult to do any experimentation in the plant. At high temperature, you cannot see what is happening inside because it is opaque, and your vessels are also you cannot really see it. But fortunately, there are principles involved through which you can actually use water at the laboratory scale to physically model. That means you can make a smaller system in the laboratory, and then for example, these information can be integrated very nicely to study what happens. So even the physical models, those understanding can be used in building. As I was telling you, integrating the knowledge, it can be very nicely done by mathematical models. And again, models are applied at different scales. Okay, it can be it can be at the scale of microns. If you are looking at how the phase transformation happen, it can be at the scale of particles. For example, if you take an iron ore, it is made of small grains of particles. So what happens at that? At the particle level, at the level of each stone particle, what happens? Or at the level of the blast furnace or the reactor itself, what happens? So there are different scales involved. And people conduct experiments, people conduct models, depending on objective. That's what I was telling you. One needs to look at different scale. And of course, again, one can try to integrate all these things to study the system as a whole. So with these comments, now let me get into some case studies. So I start with one of the raw materials which is used for blast furnace, which is called the pellet. Okay, you can see this is actually a pellet. It is typically balls of you can say 1 centimeter in dia. Okay, 1 to 1.2 centimeter dia. This is an iron ore ball. Okay, and especially nowadays there are other kinds of things, but I just want to tell you about this. Pellets. Indian blast furnace are trying to, use more and more of these pellets into their furnaces. Okay. Again, there are reasons for it in terms of production, in terms of emission, etc. So they are trying to use more of this. And also, when you mine, a lot of small fines are generated. And if you want to utilize these fines, one of the efficient methods or one of the best methods is to make them into pellets. And then, put it into furnaces like blast furnace, or there are other furnaces also like, gas-based DRI processes, we call them. So such furnaces are there. Anyway, so if you look at the process, of course, this work has been done when I was, working as LKAB chair professor at Liliu University of Technology. By the way, again, why I spend my time there is they have experimental blast furnace. It's almost close to Arctic Circle, and they have also a lot of iron ore. Even during World War, Hitler used to get a lot of iron ore from this part of the world, and that is the way he used to make a lot of weapons. Okay, so this company, LKAB is very close to the Arctic Circle. Rather, it's beyond the Arctic Circle. So now they have what is known as a magnetite ore, and they do they remove a lot of impurities from it. They call it gang. Okay, and then there are a lot of operations. Okay, so at the end, through what is known as a drum pelletizer, they make small balls. Okay, and afterwards these balls, they will not have strength, so they need to be heat hardened. Okay, they need to undergo a process where it will go through a furnace where you pack around half a meter bed of these small balls, and it pass through like a train goes through a tunnel. This goes through a tunnel, and then slowly it gets heated up, it gets dried, and then because of temperature and other reactions which is happening inside the pellet, it gets heat hardened. Okay, and that is the one which is used for in the blast furnace. So they have, for example, a furnace where they use 100% pellet. Last 50 years they have been using, SSAB is a company there, where they have been using 100% of these pellets as their charge. Okay, and now Indian furnaces are gone up to 20% or so. They want to increase it further. Okay, so efforts are there in this direction, especially because of carbon footprint and production rate, as I was telling. So please stop me anytime, interrupt me, so that if I go beyond which many of you may not be able to appreciate, please let me know. So now, they had a lot of models which is at the reactor scale. Okay, but the problem is, as I was telling you, it's a bed of 500 mm or so bed. So now, from top to bottom, the way these pellets see the temperature, see the gas atmosphere, because of that there is a variation in property from top to the bottom. Okay, and one of the problem they have is, we have to first identify what are the important phenomena which happens inside one single pellet. Okay, so so we started looking at it. See, one thing, people have conducted a lot of experiments on these pellets, but again, these experiments are not conducted. I mean, they know that a lot of complex things happen inside the pellet, so they used to conduct these experiments trying to simulate what happens in the actual plant. There are different ways to do it in the laboratory, and then try to study, and quite often it was very difficult to get a quantitative, in terms of numbers, how to get what is happening inside. This is again very important, because only if you express things in a quantitative fashion, you can put in a larger reactor scale model and then predict the quality. Okay, so somehow these experiments were not done, I will say, systematically. And because of that, the information was not available in quantitative terms. It was available in qualitative. If I add this much, okay, this can happen. So it was not very quantitative. So then we said, okay, let us look at it more quantitatively and more scientifically. How we look at, in science, whenever you have a complex system, first what you do is first identify which are the important phenomena which is governing the system, which is influencing the process, or which is influencing the system. So in this case, for example, I can tell you, there is as I told you, it's a magnetite, and actually it gets oxidized to another form called hematite, Fe3O4 to Fe2O3. So there is a process involved, oxidation, and there is a sintering, means this pellet is made of very fine small powder particles. These powder particles, they form bonds. Because of high temperature, there are again processes involved, fundamentals involved. So because of that, they form bridge between them, and that gives them the strength that is called sintering. And on top of it, there is a heat transfer which is happening inside the pellets. So how do you actually study such complex system? You study a phenomena in isolation to the extent possible. So you conduct experiments to study sintering separately, to study oxidation separately, to study heat transfer separately, and then you use the tools of mathematical models to integrate them. So this is exactly what we adopted. Unfortunately, only in 71% has done this as far as pellets is concerned. Afterwards, nobody seemed to have done such a systematic study. That is what gave us opportunity to look at things in a more systematic fashion. See, one thing I just wanted to tell you, again, coming from my background, I have, during my PhD, I was primarily a modeler, okay? And after even, as I told you, when I was with Professor Sitaraman, I started looking at experiments. And this is the first time I was designing experiments based on, my modeling background. And that gave a different, flavor, an experimentalist will do. Or rather, there are ways at which you look at things. So because of modeling background, in some sense, I started doing experiments slightly different from what others were doing it. And that made, this study something different from what others have been doing. Okay, I will tell you why I am talking about this later. So hence we need to do experiments. And how do we do experiments? Sintering, for example, is done through, during sintering, the particles, these powder particles come closer. And because of that, the whole pellet, its size decreases. Okay, so this is well known to metallurgical community. There is something called powder metallurgy, where using metallic powders, one can make, components. That's called powder metallurgy, and that is sintering again. And those people, they have conducted a lot of experiments. They have a good knowledge about this. And one of the ways of knowing how sintering has happened is through a very simple, technique, where you have a light source, okay, and then you have you keep a pellet, and you can control the temperature. You take a shadow picture, and then you can see how, as a function of time, it decreases. Of course, it needs good amount of optics and image analysis, because it's all at a small levels. But once the resolution is good, you can actually find out how the shrinkage is happening. That way, you have a quantitative way of measuring, in situ measurement. With the time, you can actually measure how the sintering is happening. This is one way we adopted to study sintering. The other way, of course, this is well known. During oxidation, it absorbs oxygen, so the weight of the sample changes. So we conducted experiments at two scales. One scale is at the powder scale, and at the other scale is at the pellet scale. So now, once you have looked at the phenomena in isolation, of course, you have to make sure that when you do oxidation, you should not sinter. So you do actually at a lower temperature. And when you do sintering, you make sure that it doesn't oxidize, or either you make sure that, atmosphere is such a way that it doesn't oxidize, or you oxidize and do the, So one has to look at things in a more systematic fashion. And that way we conducted these experiments very carefully. Okay. For example, how the area changes as a function of time is shown here. Of course, there are two phenomena again here. One, as the temperature changes, there is an expansion. So the pellet expands. So there is an expansion, so the area increases. But you can see that because of sintering, the area also, the pellet also shrinks. So there are two phenomena, but expansion can be very easily taken care. We know there is a thermal expansion coefficient, so it can be taken care. And the most wonderful thing about the whole exercise was, we looked at the literature where powder metallurgy, where people have already used, they know the phenomena, they have described the phenomena, and there are already models available. So we just thought, okay, let us use these models for iron ore sintering. That's all we did. And you look at, we did so many experiments, and all those experiments, it beautifully fell on one line. This clearly tells that those models which were developed by powder metallurgists were so nice. This was kind of, at least for me, it was a eureka moment when I saw all those experimental points falling into one line. And based on that, I'm not going into the mathematics of it, but based on that, we developed the equations. That way we could actually quantitatively describe the sintering phenomenon. So you can see that it's a combination of experiments and modeling which gave us this particular way of looking at things. Okay, so it was something which is new. As a modeler I was learning. Sorry, yeah, this is the same thing. And then of course we wanted to further do things, so we also looked at this was in collaboration with a professor from computer science, where this is a cross section of a pellet. Actually this pellet is not a, it is some thousands of images which has been stitched together. You can do all those things. So you look at very small area so that you can get the details, and then you can stitch them together. So this image is made out of that. And then there are techniques which are available in image processing, where how the bridging can be quantified in terms of images. So actually that is why we use the help of a computer science professor. And actually when we compared what is microstructurally obtained, looking at actually at the powder, and what we measured using at a macroscopic level, looking at the shrinkage, actually it was such a nice correspondence between these two. Okay? So we actually confirmed it at both levels. These are all very revealing, things where we could see that yes, what we are doing is fundamentally fine. We are checking, at different scales, we were checking whether what we have understood is fine or not. And then of course now we can predict. Once we have the equation, there are ways to do it. I'm not going into the mathematics of these things, but I'm just telling you how we use mathematics, experimentation, and prior knowledge, all these things put together to come out with the prediction, and these are how well it predicts. Okay? This is as far as sintering is concerned. Similarly, when it comes to oxidation, okay, again we did experiments at 2 scales. So again we did the studies. This shows a single magnetite crystallites or particle powder scale, and how the oxidation takes place. Actually you can see the needles which are growing in, basically Fe3O4 becoming Fe2O3. So there is a kinetics involved in this. So one needs to study the kinetics at this scale, and there are models available. Actually for this kinetics we found there is a well-known model called Avarami model, which is used in phase transformation, and that model fits very nicely for this magnetite to hematite. And there is another scale. This is the scale of pellet. I have illustrated through see, visualization is important. Again, please understand that. Okay. So you look at, here. So if you look at, actually this is already oxidized, and here the oxygen is slowly going in. Here, some oxygen has oxidized, so center it is still unoxidized is left. And as you go further and further inside, you will see that there are non-oxidized Fe3O4 or magnetite which is there. I'll tell you why we are interested in this. The sintering characteristic of this Fe3O4 is different from the sintering characteristic of Fe2O3. Rather, Fe3O4 is easily sinterable. So it shrinks faster compared to the one which is outside. So in what happens in the plant level quality, the inside is not yet oxidized, so it will shrink, and once it shrinks, it will come out of the bigger pellet. So if you take these pellets and shake, you will hear the noise like a copra, dried coconut. I don't know if you have experience. It is like that, you will hear the noise. And that is actually not a good pellet. That is a bad pellet. So you have to now control these two in such a way that you don't produce a bad quality pellet. And this is exactly what the plant wanted to do. So now you have experimentation both at the sinter, heat transfer, of course, it is well-known phenomena. I'm not going into the details. And similarly, oxidation. So we had studied the phenomena, in isolation. We have understood the principles or the laws governing those. Now you use them together to form the overall, model. And this is what is the model now being used by LKAB to look at, now they are doing a lot of experiments also. This is called the model called the spin. Okay. So this is just one case. Okay. Let me now come to the next case. Okay. How much time I have? I think I am going very slow.
So
Hello?
you can take on your time, sir. It's allowed.
Okay. Yeah.
Yes.
I'll try to go faster. I think I'm okay. The next one, which is close to my heart, is where iron blast furnace. So this is one of the photographs. I got it from now JSW is one of the largest steel plants. They have, I think, crossing Tata Steel in terms of production. So this is from JSW Bellary, their photograph. So these are huge furnaces. This will be, almost 100 meters high. So this is taken from very far. So that huge furnace. So let me tell you again why experimentation is important. Whatever understanding we have about blast furnace, okay, it is thanks to Japanese. Typically a blast furnace, my understanding, it will cost around approximately, I don't know, 1,200, 1,300 crores. A blast furnace currently will cost. Okay, and it will run for at least 15, 20 years. That much. Once you start the furnace, it will run continuously for that many years. You cannot just like that stop the furnace and start. These are all huge furnaces. You have to, even COVID time, you have to produce. You cannot, however small, you have to produce. Okay, so that's the way these furnaces are. And what Japanese did till this is somewhere in 75 or so, we didn't know what is happening inside the furnace. And what Japanese did was actually to quench the furnace. They pass the air, oxygen, air, etc. from the bottom, and there is a lot of burning happens, and that is what drives the whole furnace. So instead of that, they injected nitrogen so that the whole furnace can be, quenched very fast. Imagine, so 1,200 crores worth things, and they did not stop at one furnace. Some 7, 8 furnaces were quenched. This is the level of scale of experiments which is done by Japanese. And then, like an archaeological excavation, they went into the furnace to see what is inside. And one of the most revealing things was what is known as a cohesive zone, okay, fusion zone, where actually, above this it's all solids, and below it, it becomes liquid. So there is a zone where some solids in this become, starts to become liquid. So it forms layers. In blast furnace, we charge things in layers, and that is going to control the whole furnace, operation, all those things. This was not known at all till that time. Okay, and of course there are also measurements which were done. Just to tell you, of course, these measurements were done during our, project at NML, where Tata Steel, Bokaro, all those places. Again, making these measurements are not easy because if you want to measure the, so this will be approximately 30 meters or so. So you have to put a probe at the top, and that has to descend with the whole charge. These are all huge systems. Okay, so and then till it become molten, till that you hope that it will give data, and that way they try to measure the temperature, composition, etc. So such things have been done elsewhere also. This is one such, for example, composition measurement. And one of the things which they found out through all these measurements was there is a zone where the composition as well as actually temperature, this is that place, temperature remains constant in the furnace. Then people understood through thermodynamics that it has to do with thermodynamics. Okay? And then based on this, a theory of blast furnace was developed. The current way we understand blast furnace based on this theory. And using this theory, one can actually make a very simple model. Okay, this is called the RIST model, which is a very simple model one can make. Okay, again, I am not going into the details of model. It is based on heat and mass balance, and so that's why the furnace is split into two reactors. For chemical engineers, they'll be able to appreciate what I am telling, into two reactors with at the middle where we know things, because thermodynamics tell how the thing should be there. So we know things at the middle, and based on that, a model was developed. Now, these models can, very simple models, but these can be used very nicely. For example, recently, we have used this model to study, how much natural gas can be injected into the blast furnace. You may be wondering why natural gas. Basically, we want to bring down the carbon emissions. So we want to replace the carbon with something which contains more hydrogen. So one of the option is natural gas. Of course, India don't have that much amount of natural gas also. Rather, even the carbon which we use in blast furnace, we are importing it. Okay, we have iron ore, but we don't have carbon which can be used in blast furnace. So we import it from Australia, South America, all those places, we have to import. But then ExxonMobil, they were interested. They thought that, they will have a good business if India is going to go towards lower carbon emission. ExxonMobil is somebody who deals with natural gas. I think you would have seen in advertisement comes in, in TV, etc. CH4, they promote that. So they wanted to explore the possibility. So this was funded by them. And then we used this simple model. Again, I'm not going into the details. We used this simple model, and based on that, using Indian raw materials, for, as I was telling you, Indian furnaces are also going towards pellets. Indian furnaces are also, trying to reduce the carbon emissions. So they want to use more, natural gas. So how much natural gas can be injected into the blast furnace for different conditions? So actually, again, I'm not going into the details, but I'm just telling you how a simple model which is based on heat and mass balance and understanding. Please understand, there is an understanding which has come about from that experiments as well as all those things, and based on that we developed a model. Now we can predict. At least this becomes a useful tool to try out now experiments. Okay, it may not be exact, but still you can at least your window of experimentation. You get a feel. Okay, how much can be injected? At least the first knowledge is available, and based on that one can try. Okay. And of course, this is a simpler model, but then as I told you, to predict the Cauchy zone is one of the most difficult tasks, and that is why as I was telling you, it was my dream to get into this, and for that we started with NML, and that is where my modeling as a professional or academician started. And that was really a great experience. See, one thing I can tell you is blast furnace is a very complex reactor. Just to tell you what all phenomena happens, there are solids which are moving down, and there are layers, there is a gas flow. So, there are powder, there are, two kinds of liquids which drips through this furnace, and these are all high temperature. So, it's really a very large complex system. And commercial softwares, like Fluent or many of those things, these are not very amenable, or these are not very easy to implement these things, such large complex systems. There are reasons are also, okay. Those who know fluid dynamics, heat transfer, mass transfer, the interconnectivity between these equations are quite large. And because of that, these are very difficult. So at that time, we developed ourselves, we wrote codes and all those things. And that is the way my journey into blast furnace modeling started. This shows the complexity. But when we developed ourselves, it had its own problem. And that's why I told you it was still a baby, but it was some 7-8 years we have spent just writing our own codes. Okay. Then came, an open source software called OpenFOAM. Okay. This OpenFOAM, the thing is, the source code was available for free. That means you can do what you want. So many of the things are already available, and then we could implement the same thing, whatever we have learned through that NML, that large project. All those things we could implement in a better fashion, more efficient manner through this OpenFOAM. And that resulted in what is known as BLASM. This was sponsored by Tata Steel. And now I can tell you, we have a robust model. Though I am telling this in words, but it has taken more than 15 years to come to this particular stage. Okay, and so many students, involved in this, so many researchers involved in this. So it was a mammoth task, but I can tell you now we have a robust model which can be tried out by the plant. You change this, how the cozy zone is going to go down. All those things can be done. Now Tata Steel is exploring how natural gas can be injected, and not only at there are different levels in which they are trying to now inject. So they are planning to use this model to try out these things. Again, I am not going into the details, but it has been a great learning experience for me or for many of us, going through this. But why I brought this is, again, so many researchers have done so many experiments on different aspects, how an iron ore will reduce, how it is going to melt, how gas flow through a bed of particles. So these are all different experiments done to look at different aspects of the system. And what the model could do was to integrate all those things systematically to understand the whole system. So that is what we could do through this model, of course. And also we learned a lot of parallel processing, because these are highly computationally intensive. So we implemented these things in a parallel. So now it works in almost half an hour or so it takes. When we developed at that time, it used to take almost 15-20 days to get one solution when we developed at that time. Now we can do it in almost half an hour to get the converged solution. Okay, so I'm not going into the details of it. These are all different things you have validated and all those things. I'm just showing you some pictures which shows different temperature profiles and all those things. Okay, so let me come to probably the last topic, which is also, give me another 10 minutes. Is it okay? Hello?
Yeah, that's
Yes,
fine.
sir. Yes, sir.
Please go.
Yeah. So again, one of the issues in blast furnace we learned is, below the, I was talking about fusion zone. There is a zone where, which is called the dripping zone, where the hot slag and the hot liquid metal, it drips through, the particles of coke. Okay, this is called the dripping zone. Okay, now this comes on the way of production. I'll tell you why. Blast furnace always want to produce more and more. And the issue is, the gas has to go up through this bed, and the liquid is dripping through this, down. So now, this because of this dripping, the gas is not able to flow easily. Rather, there is a very nice experiment done in somewhere in 70 by a person known as Sherwood. What he did was very simple experiment. He took pebbles, you can say stones, in a small, you can say bucket or some small tube kind of a thing, and then he allowed water to be dripped from the top. This is like liquid metal dripping from the top, and then he passed, air from the bottom. Now, what he did was, for example, suppose he maintains the water flow rate same, and then you keep increasing the air flow rate. Okay, and of course he can measure the pressure across the bed and all those things. At one point, the water cannot come down. water cannot come down. Water actually will overflow. So, in blast furnace, if such a thing happens, the liquid will not come down. Okay. So this he found out, this is called flooding phenomena. It's a very simple experimentation. That's what I was telling you. First is to understand the system, then you try to quantify. It was such a simple experiment, and he did it. And based on that, he came with the flooding criteria. He did not do it for blast furnace. He did it for some chemical engineering system. But even now, that is used for understanding blast furnace. And there is also another interesting thing he came out with. Suppose, I have this liquid which is there, and I am passing the air from the bottom. Now I suddenly stop the air. Okay, then the liquid will start coming out. Okay, it will drain. But there will be some liquid which will be always stay inside the system because of surface tension forces. Okay, and this is again very important in blast furnace, because that is called the static holdup, which stays with the particle. That means it moves with the particle. It doesn't move relative to the particle. Okay, so it is always with the particle, and this plays an important role, because slag has a tendency to hold with the particles more compared to liquid metal. That means liquid metal will drip like water, but this slag will be there like, I don't know, something which is more sticky. It will be there with the particle, and this has a lot of things to do with blast furnace. So again, no fundamental study people have done up to this level. So we wanted to look at this in a more fundamental understanding. So what we did was a very simple experiment. This was my PhD student who graduated some time back. What she did was she took 2 spheres. These are quartz spheres, and then you inject a small amount of water and find out what is the maximum water which can be held between the 2 spheres. Just to show you, of course, these are all micro syringe which has 2.5 microliters. So I can just show you the video. So actually you can see already there is some amount of water here, and you are injecting water. You find out what is the maximum amount. So you keep injecting, okay, it is staying. You keep injecting, it stays. Now actually this video will show, we are about to inject, it is just at the maximum. Sorry. Yeah, you will see injecting. Sorry, I made a mistake. Give me a second. Yeah, see, it has dripped. Okay. So basically we can find out what is the maximum the liquid can be held between 2 spheres. And not only that, once the liquid goes down, there is some amount of liquid still remains at the contact. So there is a remaining liquid, there is a maximum liquid which can be held. So this can be done very nicely using experiment, using different balls, different liquids and all those things. We can study it fundamentally, the phenomena. Again, you have to do experiments. So she did a lot of experiments with different inclination. This is the maximum liquid which can be held, between 2 spheres. This is the liquid which is remained after it has dripped down. These are the 2 kinds of, Why are we doing with 2 balls? Now, a bed of particles, a bed of pebbles can be looked at as, 2-point contact with different orientation. So once you know for different orientation, now we can extrapolate to a large bed. And that is why we did this fundamental experiments. Not only that, we know the physics of the problem. It has to do with surface tension. It has to do with gravity. So there are techniques available in energy minimization. So I'm not going into the details of the mathematics. Once you understand the phenomena, you can write the equation. So it needs to be solved. And how did we solve it? Again, we have to go to a computer science professor to take the help, because it is like, you take a small cylinder between these 2 spheres, and now you make into triangular meshes. Again, there are nice softwares, open source software available, because triangular meshes are used for creating geometries. One of the ways of you can create complex geometries, animations, all those things. Those people who work on those things, they use triangular mesh because it can represent things. Okay, so we use that. Okay? And what we do is we actually change the shape of the film, using this energy minimization technique. Okay, you have to keep on bringing down the energy, and only those you accept. There are again algorithms available, and based on that you can predict what will be the shape, final shape of the liquid. Okay, and this is again a very complex, highly computational intensive. So this has been implemented in parallel processor, all those things. So I'm again describing in simple terms, but but there are a lot of work involved in doing so. And actually we could exactly verify, whatever experimentally we got, same thing we got even computation. And then we could get, different, different shapes, and we could see at what point, it is going to come out. What is the maximum amount which can be held? So these kinds of computational techniques were used even, for example, some systems, though the two balls are symmetric, but the liquid form, which is there between, it can become asymmetric. We got it experimentally. Actually, even the model actually gave those results. Okay, these are all very interesting results, which we didn't expect at all, and which was very thrilling for us. And then we could even validate, the modeling results with you can see this is the maximum volume model and the experiments. It was nicely falling into one curve, and with that we came out with dimensionless expressions, which is again a useful thing for people, for engineers who develop packed bed, dripping, beds, etc. So they need in a much more macroscopic form. So we could come out with expression. And similarly, to find out the remaining volume after dripping, we need to get into the dynamics. So again, we used open form, which involves CFD and all those things. Again, I'm not going into the equations, but it is like, you add a drop of liquid, and then how the film is going to get disturbed and how it is going to flow and all those things. So all these things, open form things were available. Again, in parallel processing, we have to run. And based on that, actually, we could predict also what is the remaining volume. You see experiments as well as modeling results. It's a combination which has resulted in this. And based on that, actually, we came out with an expression for the static hold up in blast furnace. Actually, when I was presenting this in one of the conference, molten slag conference, so one of the, Korean professor asked me, are you telling that just doing experiments with ball and water, you are telling that you can predict things in the blast furnace? I said, you look at the results. At the end, what we need to look at is the phenomena. Okay, so if you try to understand the phenomena, then model it. So then you will be able to understand things, and that way we could actually come out with an expression for the static, and there are also things beyond it. I don't want to get into the details of it, but I can also just tell you, using the same principle, if I have a bed of particles, let me say, I have small balls and big balls. Now, if I decrease the size of the balls, in a smaller ball, it is more difficult for the liquid to drip. Okay, bigger balls it will easily drip, smaller balls it is more difficult to drip. Now, what is the implication in for example, in blast furnace? There is a size of coke, in the bottom part of the blast furnace. If you go below a particular size, you cannot remove the hot metal. It will not come easily. This is a problem in the actual plant. So now, what is that size which needs to be, which can make sure that it will actually come out? Actually, we could find out those size using this model. Again, I'm not going into the details of it, but if you go below the particular size, the liquid metal will not flow through the bed. That means you will not be able to take out the metal. So these kinds of things can come out using a judicious combination of modeling and experiments. just don't want to get into the last one, though it was a very simple one. So let me end my talk by saying I hope I am able to convey neither modeling alone, which is the way I started when I started my research. It is building model in air, nor performing experiments without quantitative focus. So I am also critical about people who do blind experimentation. So I think a modeling attitude is very good to conduct experiments. Similarly, people who do modeling should also know, the experimental adjustment. So it is a judicious combination of both is what I feel is scientifically or technologically it will be a fruitful exercise. That is all my concluding remark. I hope you could appreciate whatever I was trying to convey. So thank you very much. So yeah, any questions are welcome, please.
Thank you, Professor Viswanathan, for your insightful presentation. You have exposed us to the dynamics of system modeling and simulation. Now we can take queries from the attendees. YouTube attendees can post their question in the chat section. Those who have joined us through MS Teams, they can raise their hand and we can take up the questions to Professor Viswanathan one by one. Yes, is anyone there from the MS Teams? I think there is one question from Vishwateja. Yes, Vishwateja, you can carry
on. Can you hear me? Am I audible?
Yes, you are audible. You can ask your question.
Professor, that was a very insightful lecture. Thank you for introducing the concepts of blast furnace modeling and how modeling is done with this particular case. One question I have is that as far as the blast furnace modeling goes, the two-dimensional system that you have developed, has any work been in progress to create it into a three-dimensional sort of a way, or is there any requirement to do so in the first place?
If there is a requirement, yes, there can be a requirement. I'll tell you why. There are two aspects to it. Especially at the bottom part of the blast furnace, the gas is coming through discrete, what is so-called tuers. Okay, so the flow there is a two-dimensional flow. So if you, three-dimensional flow. So if you want to capture this particular flow, then you need to get into 3D. Actually, we did 3D only the gas flow for Tata Steel. For example, sometimes they have to close down, or they call it blanking, one of the tuers. And then what happens at the bottom of the furnace? So only the gas flow we have done. But yes, if you want to study especially the bottom part, then that is needed. And the other problem is the cozy zone, which I was talking about. It can become asymmetric. If it becomes asymmetric because of the charging, any of those things, if it becomes asymmetric, again, the need for 3D will come into the picture. I can tell you now, with the confidence, we have developed over the years, I can tell you this BLASIM model, among the models available, there is a Japanese model called Bright. There is another model called, model from Europe, Mogador. I can tell you, compared to all those things, this model, because it uses one of the latest numerical techniques and all those things, it is, at least I find it one of the best models available in terms of, number of grades, the minute details in which you can capture things. So that way, this can be surely easily converted into a 3D model. So of course, that is, I also look forward to it, but I think people have to get it. And let me also tell you, but modeling alone is not going to help the purpose. Again, what India needs is also, we need an experimental blast furnace. because we have to conduct trials in those experimental blast furnace. So the Sweden I was telling you in Luleå, they have the furnace where they have conducted experiments on hydrogen. All those things have been done. Every 6 months they quench that small furnace and they, look at how things are. Okay. So I have been telling that we have so many mini blast furnaces. So I think, industries have to come together, R&D, all those people, and we have to adopt one such small furnace, conduct those experiments, then only we can develop technologies. Why Japanese could do it? Why now Sweden is doing, they are able to produce, without carbon, they have produced steel. It is all because they have spent a lot of time and effort doing these experimentation. We also need to do. Modeling alone is not going to help. This is exactly what I am trying to tell.
Thank you, Professor.
Yeah.
I think Vishwateja is having one more question. Yes, Vishwateja.
Of course, I understand, sir. If every good model has to follow through with an experimentation, and the basis of modeling itself is the experimentation at a laboratory scale.
Yeah.
What I'm trying to understand is what kind of a scale of is the mini blast furnace that you're talking about? You keep mentioning that we have we have mini blast furnaces around. We could try and see if we can quench them and follow through with an experimentation.
Yeah.
What is the scale of this that you're talking about?
Yeah, so what I'm talking about is, we have, for example, mini blast furnaces which produce 100 tons per day. Those kinds of furnaces are available. They make this cast iron pipes. Okay, so I know many such furnaces are there. Now, what I am telling is, of course, these furnaces, I have an idea about it. Of course, I have discussed this with Dr. Bandyopadhyay a long time back. The idea is, there should be a business model to be put around this. These are not small experiments. So where one has to instrument these furnaces, one needs to run a campaign. This is exactly what, in Luleå they do. They run a campaign for 6 months. These are the things to be planned. At the end of the campaign, they quench the furnace. So we have such furnaces already available. Means it's there in the country. Many small such 100 tons per day kind of furnaces are available. One needs to instrument this because then only we can get the data. And we cannot just like that operate one day and stop it. Blast furnace cannot be done that way. So it has to be continuously operated. So that means this should be production come experimental unit. Are you getting my point? Then only this model will work. So we need to think, much more than just experiments. We have to think, we have to build some kind of a large business model or management model, whatever you call it. Then such things need to be tried out. Then only, we can make, and such things are being tried elsewhere. This is exactly my point.
Thank you, Professor. There is a question from Dr. Yamuna Rani. Yes, Dr. Yamuna Rani, please.
I think she's muted. Yeah.
The talk was very interesting, and it was actually giving a mindset how you should be when you are going to take up a modeling exercise and then use it for simulations, and also the specific terminology, nomenclature, and all that, how it should be used, or not to get confused. And one question which I wanted to ask was, okay, you propose a hypothesis, and you are, according to that, you are coming out with the model, and you are trying to validate it through experimentation. Now, it is not always possible that the model you develop is going to actually match your experimentation. It could be in the neighborhood. So, I mean, is there any way that you can actually find certain set of, because what we do is we try to find certain set of parameters which are going to match the experimentation while retaining the theory. So, in that direction, I mean, there are certain, like when we do kinetic modeling, you're going to do the parameter estimation, whichever the RNS constants or whatever it is, there are a set of parameters which you determine through experimentation. But if you are going to propose a theory based on multiple models at different levels, whatever you are going to combine to make it into a total model, it is possible that the combination as such might not work efficiently. There could be some loopholes. Do you Did you experience such loopholes where you had to incorporate certain additional sort of manipulations, not in the sense of manipulations in the wrong sense, but to make the model match the experimental results? What are the additional efforts that you need to put out? Because that happens quite often when you're going to do a modeling exercise based on experimental data.
Yes.
Like, for example, there are heat losses which are ignored in most of the cases. I mean, when you're doing experimentation, heat losses to the environment, if there is a very, especially when you're looking at high temperature systems, so heat losses are not very well captured. That is going to take up a considerable amount of energy, which is not accounted for properly in the models sometimes. So such things, I'm not specifically referring to one situation. But
Yeah. So see, just to give you, I'm getting different thoughts. So let me just tell you one experiment which people do is in TGA. Okay. Now, in TGA, when we do high temperature experiments, okay, we may be passing a gas from the bottom, and the sample may be at one temperature. Now, quite often, the gas may be coming at a lower temperature, and then when it touches the sample will be at a different temperature than the furnace. Okay. So now, because of that, I know that there are a lot of data which is reported wrongly because of this particular experimentation being wrong, and people have corrected these experiments. Okay. For example, what you do is you heat the the gas before it gets into the TGA. So you can use a bed of particles, alumina particles or whatever it is, to heat it. Okay. So what I am trying to say is, you hypothesize, you may have a model and you have experimentation. They learn from each other. I think this is again a modeler learned from the experiment learned from the model. So there has to be this has to evolve together. That's the only way.
yes.
Just to give you another example, I was talking about the static hold up which I was telling. So the word static, people first thought it had to do only with interfacial phenomena. And so they were trying to correlate, the static hold up with only interfacial phenomena. Now, only one or two experimenters, they said, no, it has to do with viscosity also. Okay. Now I can tell you why it has to do with viscosity also. Because though we are talking about, static hold up, I was talking about, what is the maximum volume which can be held between the spheres, and what is the volume which will get remain after it get dripped. Now in a packed bed, it is going to be a combination of both. So now, because of this fundamental experimentation, actually now we know that why it depends on kinematic viscosity also. So in a way it gives the clue, okay, now why we need, we got a reason, we have to include the viscosity into our correlation, and that is exactly what we are suggesting. So actually some people were not including viscosity, thinking that it is only a static phenomena, and some people did include viscosity without knowing why it is so. And now the experimentation and all these things have given an insight, okay, why we need to include viscosity. So I think we all learn that way, the system, model and system has to go nicely together. Actually, there is another nice, present graffiti by Professor Aris Rutherford, where he talks about, experiments and modeling, how they learn from each other. So I think that's the only way, and that's the only way to, we have to keep improving each other. That's the only way. Yeah.
Thank you.
Thank you, Professor. There are some words of appreciation from a YouTube attendee, Gayatri Naresh. Thank you, sir, for giving us a deep insight on blast furnace modeling. Is there any more questions from the MS teams? Yeah, Dr. N.V. Satyanarayana, yes.
Yeah, I think the memories are live. We made live memories of the way we were working. But then I always had this feeling because when I was working on the raceway zone, we were having a particle image velocimetry and then doing the trying to visualize the flow patterns. I felt that among all the zones where you need to model, the most difficult one was the raceway zone, especially considering you do not know any idea of where the dead man region lies, and also the particle size of the pulverized coal also varies, the ignition and all. So though we tried to come out with a visual a model, I think we are not really successful. Of course, it was good for making some publications, but then in reality, I don't think we could have applied that to when you are looking at a real-time process simulator. So have you subsequently worked on the raceway zone at some point of time?
Not really. Raceway, I have not. Means I have come up to only dripping zone from the top to the bottom. So now maybe I will get into raceway zone. I do understand. Even in this model, I can tell you we have assumed the shape of the raceway. So we didn't explicitly model the raceway dynamics. We have not done it. So raceway is still. I know Professor Govinda Gupta of IISc, he has been looking at through experimentation, the raceway. But frankly, I have not spent time looking at the raceway dynamics myself. Yeah. So I know things are complex, because there is a fluidization, there is a packed bed, all those things come into the picture. But not really, I have not spent or experiments or nothing has been done on that direction. Yeah. But I know it is also very interesting. Yes.
Thank you, Professor. From my end, one question is there. Although I am not from a chemical engineering background, but the question that arises at the back of my mind is about the fault tolerance, because these are very much real-time systems that you are designing and simulating. How do you introduce this fault tolerance into the system?
Okay. So let me tell you that's why I was talking about simple as well as complex models. The complex model for blast furnace, which I was telling, it cannot be used as an online tool. No chance. It is only a you can use it to study, for example, how much if I inject natural gas, what is going to happen. Those kinds of scenario studies and maybe training of people, etc. That can be done. But on the other hand, if you want to look at something which has to be used online, or that is why I was talking about a simpler model called risk model. Or actually, I didn't get the time, I stopped it. We developed a very simple model for bell annealing furnace for one of the company called Thies Precision Steel. It's a very simple model. Only thing is, there are already experimental, parameters or thermocoupled readings, which is given out continuously, and that is taken out, and that is used to tune the model adaptively, dynamically. Are you getting my point? So in a way, the model adjusts itself. So that means these models have to be fast. Okay. So that kind of things have been done. I can also tell you another, which I was not involved, but one of my colleague from chemical engineering was involved. For Tata Steel, they have the continuous annealing line. Okay, where the sheets goes through, this continuous annealing line. So for that, the heat transfer simple model was developed. Then they used the principles of this control, so it's a judicious combination of theory and, I don't know what kind of control it is, statistical control or whatever it is. I don't know the details of it. But they made a combination of that, and they have developed now a tool which is an online tool. So, so hence, depending on the situation, that's why I said the models, we have to know the objective very clearly. And depending on the objective, the model has to be complex or simple, because if you want to be an online system, it has to be simple. I'm not ambitious to think of putting a complex model into a system, at least at present. But I don't know, nowadays people are talking about artificial intelligence, and twin, what they call it, some twin system, where the actual system will be there and there will be a twin which will be, simulating the actual this one. So I don't know, people are ambitious. Yeah, I don't know how that is going to come, whether we can get into that level. Maybe, maybe another 10, 20 years, we may be able to get into that. But yeah, that is the direction in which we would like to go, to integrate everything. At this stage, simple models with some kind of statistical or those kinds of tools, AI or whatever you call it, those tools have to be judiciously used for online control. That's what my general understanding is.
Thank you, Professor, because this question was actually, we have a subject in computer science and engineering regarding the modeling of this real-time systems, where we talk about those fault tolerance. So this question was related to that context.
Okay, I have just one more comment. Nowadays, this data science, data mining, and all those things have become a buzzword. I'm not critical about it, but at the same time, it has become a word everywhere. But see, that cannot, just because these are there, we should not, ignore the fundamentals. At the end, some theory, fundamental, that are also equally important. It's again, just because these are available and people think that this data science, data mining will give all your answers to all your solutions. No. Then, whatever we study, in the engineering, those principles, everything become irrelevant. I think it cannot become irrelevant. I think people have to be very careful. Again, one should use both these things in a judicious manner. Yeah. So there are usefulness for both. Yeah.
Thank you, Professor. We have a question from Dr. Akbar.
Okay. Akbar, yes.
Professor, very interesting talk. Thank you for reminding after so long about the blast furnace. I forgot for the last 10 years. Yeah, you are saying you are right.
Akbar, don't say that you forgot blast furnace. You don't forget.
The digital twin, actually,
Yeah.
you said that is the digital twin technology, which is going to play a major role, particularly in most of the processes. JFE, it is a company, steel company of Japan, very well-known company. They are introducing now cyber physical systems.
Okay.
Looking both physical as well as cyber parts. Due to advances in sensors, image technology, and then communication. So now they are coming out tools for blast furnace using modeling. Modeling is a core of that thing, core part of that sensor, and the computation has raised like anything. In a few seconds, you can execute many of the things which we were trying to do, which we were taking even half an hour when we developed the models. But now in a fraction of, there is a hardware, very high computing hardware is available. So these things are possible. So how do you look at cyber physical systems approach to the blast furnace? Already people have started working in this direction. In India, how do we plan if you want to catch up this technology?
Yeah. See, I think we have to work together. Means
Yeah.
we have to see, again, if you look at Japanese, whether it is artificial intelligence, all those things, they implemented, a long time back in blast furnace. It is not that,
Yeah.
they have done it long time back. The other thing is we need to collaborate. See, the other thing is everybody cannot be expert in everything. We have some expertise in different things, and people have to come together. I think,
Yeah.
and make things work. Again, let me tell you, in this blast furnace model also, one of the great things we could, why we could come out with a robust one is the experience, of course, we have gained in the modeling through, looking at blast furnace and looking at the equations, etc. And there is another company in Pune called Tri-Diagonal. They have been working in CFD for a long time, and they have been using open form themselves. So they were expert in CFD and open form, and Tata Steel, of course, operational data were there. So actually, we three almost every week we used to meet for 2-3 hours, and that is the way this project, we worked for almost 2 years continuously, and that is where this model could come out. So what I am trying to say is, if you want to achieve those tasks, we have to accept expertise, acknowledge expertise of different people, and respect those expertise and come together. This needs to be done, and then only such things are possible. I think industry is trying to do. I know that Tata Steel is now, this industry 4.0. In that, this one, I know that they are trying to do such efforts. Even JSW has understood that they have to contact different agencies and put them together, such tasks. Let me also tell you, I'm talking about people collaboration. That is very important to achieve this. It is not one person. Just to give you one more example experience, when I was working in Sweden, they have, when they do the projects, any idea, for example, they will always plan it at the academic level, at the pilot plan level, at the at the plant level. Okay, pilot plant, academic level, and or laboratory level, and the actual plant. Now, when they make the project itself, when it is an academic or laboratory level, the team leader will be from academics, but always the industry person as well as the the pilot plant person is there in the system. And when it goes to the pilot plant scale, again pilot plant person scale, person takes the lead, or that organization. The others are there in the loop. So till the implementation, everyone is there. Only thing is, depending on which level it is getting implemented, people take the lead. Again, I find, unfortunately, in our system, we have not developed such matured systems. Then only I think we can, implement these things. And these cannot be done in 2-3 years. This needs time. So I think we have to realize these things and understand and work. I don't know whether I am answering your question, but this is something which is larger issue, and then only we can become leaders. Otherwise, we'll be buying technology from outside, unfortunately.
Thank you, Professor. Is there any questions from the MS team?
I just want to tell you one more thing, since I remembered. Sorry. I had a student who worked from China, with Professor Sitaraman. She worked for a PhD injecting carbon monoxide into iron, chromium, carbon melts. Okay. She did wonderful experiments in induction furnace, and we also developed a simple model for that. Okay. That was some 15 years back. Now she became a faculty in Beijing University, and now she has taken the whole concept from here. Now she is injecting CO2 into BOF, into this ferrochrome production, also low carbon production. She is injecting CO2. Now, when I look at, the idea was there, it was proved in the lab. They have taken it. Chinese had taken it. The idea was from IIT Bombay and Royal Institute of Technology. They have taken it. They are telling that they are achieving much better dephosphorylation by injecting CO2 into the into the BOF. Now you look at why we are not able to implement. The problem is, we have not come together, unfortunately. Yeah, sorry. Yeah, I finished my comment. Yeah, please.
Yeah, thank you, Professor. Is there any question? Uh, Now I request Dr. N.V. Satyanarayana to give his concluding remarks.
Thank you, Professor Viswanathan. It was very, very useful talk, not only for me, Akbar and Devjot who have joined, and there are a few others who have joined from NML. So it is actually refreshing of what we have done. But I refuse to accept what Akbar has said, that he has lost his memory. So we all worked in, so this will always be there. Now, coming to the talk, I think certain things were very well detailed, especially because this particular lecture is also being, some of the students are also into it. Many of them, in fact, I can say. So when you are a student and then when you want to attack a problem, you get mired in the details. So that is something your maxims have actually, on modeling have actually dispelled that. Don't think about the elephant the way the blind man, four-blind men visualize. Come to a point and then look into it. So the saying is also there, the deviling the details, but then keep those details away. Let the devil be away. Look at what you want to what you want to model. So in that manner, in that context, the model where you are looking at the static holding of liquid is very, very exemplary to start with. Because if you just try to visualize it, the viscosities are different. Even if there's a liquid that is dripping down, the viscosities are different. The burden size is different. The morphology is different. The type of air pressure that is going on is different. So if you just keep looking at it, you'll not be starting anything at all. So it's a very simple model, which this person has started. I think we must really. That's one classic example of how modeling should be done. It always goes from little known things and then unraveling things which we do not know. And one other maxim of yours I really liked is, again in this context, avoid rigor like plague.
This is not mine. This is Professor R.S. Rutherford. Yeah.
Oh, okay. So it only leads to rigor mortis. And sometimes, at some point of time, you also need to neglect small terms. That's also some of the maxims that you've said. And these maxims is what the total takeaway of modeling is when be it students or researchers take up this particular task. And thank you once again, Professor, for coming. And then maybe we'll have more interactions. And then one final comment, on this is you did talk about data analytics and all. So as you rightly said, these terms look very fancy, and then people think that with data type of data amount of data that you have, you can virtually attempt anything. Well, to a certain extent, it is true, but then how authentic is the data? That's something that one need to look into. And I always believe, because we also, all of us have, besides modeling, we also try to look at the physical model, try to do some experimentation. So whatever modeling we do, we must also go to the bench and then see that it is properly validated with planned data. In fact, that's what all of us have done for the blast furnace modeling. And also some of the case studies that you have discussed. In all these cases, you did have the planned data to validate it. So data modeling, data analytics, all these things will have any meaning, so to say, only if they are properly validated, the data is really authentic. This is my final take on this. Thank you, Professor Viswanathan, for being with us.
Thank you.
And let me thank all the attendees also for that.
Thank you, Dr. Satyanarayana, for your concluding remarks. Let me propose a vote of thanks before we end the session. First and foremost, I am thankful to Professor NURNI Viswanathan for accepting our request to be the invited speaker for the lecture series. I would like to thank each and every one of you who have joined us today through MS Teams, YouTube, and Facebook. The idea of having this lecture series is to commemorate the contribution of Dr. N.V. Satyanarayana, Chief Scientist and Head, Energy and Environment Engineering, who is superannuating this month. For placing the LS series on such big pedestal, I thank IEEE PES, IAS, PELS, Hyderabad Joint Chapter Section, IEEE Guntur and IEEE Anantapuramu subsections for their spontaneous support. Let me take this opportunity to thank Professor Harinatha Reddy, Professor Y.V. Siva Reddy, and Professor S.V.N. Lalita, the chairpersons of the 3 sections of the IEEE. I express my gratitude to Dr. S. Chandrasekhar, Director CSIR-IICT, for his support and encouragement to organize the lecture series. I also thank the organizing committee members, Dr. A.G. Rao, Dr. Venkat Mohan, and Dr. Chandrasekharam of my institute for their guidance. I thank my fellow colleague Sri Raghunarayana for his effort and time in preparing the groundwork for hosting the LS series webpage developed by me on the CSIR-IICT website. I thank Sri Radhakrishna, who heads our computer center, and his team for making the lecture available on MS Teams, YouTube, and Facebook platform. Before we end today's session, there is an announcement for the next upcoming lecture. The 12th lecture of the LS series is tomorrow at 11 a.m. The lecture is on AI, ML, and data science, a unified theory by Professor V. Ravi from IDRBT. I request you all to join for the next lecture tomorrow. Have a good day. Thank you, Professor Vishwanath.
Thank you. It was a nice experience. Thank you. Thanks.